Good morning, everyone. I'm Nitin, a second year undergraduate at IIT Madras, pursuing BTech in Electrical Engineering. As a part of Electronics Club, I am here to introduce you to the topic Fourier series and transform. So, in the previous session, we this is the second session in the module of signal processing. In the previous session, we had a broad introduction to signal processing as a whole. In this session, the upcoming session, we'll be discussing more about the mathematical concepts in signal processing. There's a lot of math, but we'll try our best to make it a bit intuitive and visual. So let's start. Fourier series over here is like an expansion formula. Like I'm sure you would have gone through a lot of formulas in your GE, like sin x expansion or cos x expansion. It's also an expansion, but a bit more general, which can be applied to any series that is periodic. And Fourier transform is another mathematical formula that we'll soon see. So first, let me give a few applications of this Fourier series and transform to get started. So like basically over here, this is used in image analysis and shape recognition. In the previous session, like what we did was we drew squares and rectangles around squares and rectangles and circles around circles. So this is also a primitive technique that can be used in that process. Currently, this is not being used. Rather, deep learning models are being used, but this is also a really good technique to use that. And also sound editing. Wait, let me give an example about image analysis first. For example, there is this car over here. Like by applying our Fourier transform, we can basically get a we can basically get the outline, the edges of the car by applying Fourier transform. Let's see how in a while. And also in sound editing, generally when we record audios, there's always a noise. So like there might be a high pitch noise or a low or some high amplitude sound. Like you can filter out those by using this Fourier series and transform. So now getting back to the session. So these are the contents of the session. First, we'll start with signals and systems. Like what are signals? Just a recap. Then it will be about Fourier series, a visual introduction. Like we'll see what is the Fourier series and how does it actually work. And then like we'll answer the question, like why do we need this mathematical formula and like why the Fourier series is so important to us in signal processing. Fourier series is actually a very important and core concept in signal processing. And the third module and the third part, we'll see why is it actually important. And then we'll get an introduction to Fourier transform, ending with a slight introduction to convolution. Convolution is a mathematical formula which is a little similar to multiplication and addition. You'll see it soon. So before getting started, okay, let's get started with signals and systems. Basically, a signal is information. For example, take a running man. If a man is running, like in kinematics, you might have seen that he has velocity and acceleration, displacement, and we plot all that information. Similarly, like all those plots are basically information. Similarly, here signal is equivalent to information. So velocity, acceleration, all are information over here. And systems are processes. They process the information in signals. For example, you have velocity. But like to actually make use of velocity, you need to process it to get other information, right? For example, you can process velocity by differentiation to get acceleration. So systems are basically processes. They're nothing more than that. Just like a signal undergoes a process. So that process is a system. And systems have various categories, linear, causal, stable, time invariant, invertible, memoryless. You don't exactly need to know about them in this session, but just keep them at the back of your head. And when it comes to convolution, the topic that's going to be at the last, we generally talk about linear time invariant systems because these systems are really common. Basically, what that means is that linear is basically that it's linear. Like there is no x square term or x cube term. There are no exponentials, but only linear terms. And time invariance just means that If at any moment you can describe a function with a particular formula, it should be the same throughout the time interval. For example, there is a sine curve. It should be the sine curve at minus infinity and at plus infinity. It shouldn't change its definition in between. But like that is not really necessary for this session. So let's leave that. But at the end, remember that all these signals and systems are just functions. They might carry some meaning, but while calculating them, they are just functions. Signal is a function, and system is also a type of function, but a little different. Let's see how is it different. Any doubts so far? If you have any doubts, you can put it in the Q&A panel. Okay, let's continue with that. So now we'll go through the a bit visualization of signals and systems. So basically, this is the process called the system, and x of t and y of t are input and output signals. And again, input and output signals are just time-dependent functions. Well, a system is not exactly a function, but something called a functional, which is the same as the function, except instead of like, for example, x of t takes t as input, a functional takes x of t as input. Nothing much, just that. So over here, let's take the example of a system called differentiator. Sounds different, but it's just differentiation. Nothing complex, pretty simple. So for this part, let's go to Google Colab. Like we did in the previous session, we are going to use Google Colab for coding. You don't need to actually implement the code. You can watch the code, that's enough. Or if you want to implement it, you are fine. It's fine. You can definitely do it. So if you want, the link will be shared in the discussion forum and in chat of Google Colab. So once it's all right, I'll give a little of time for those who want to do the code to open Colab. And once you're done, let's get started. Put a thumbs up if you're ready for me to start. If like Google Colab is asking for the share request, I guess just open your own Drive account instead of like this over here is using my Drive account to open this notebook. Just go to Google and search Colab, Google Colab, and you'll find this. Over here, it's signed into my account, so probably that's why it's asking a share request. So just Google it, Google Colab, and like just open it. If you have any doubts, ask it in the chat box or Q&A panel. So let's get started with this. Like first, we'll be using two libraries. One is matplotlib, which is used for plotting. Another is NumPy, which is basically all related to numbers and calculations. Just a minute, guys. If you actually want to view what I'm coding, you can now view it with that link. And if you want to code what I'm doing, then you can do it by opening your own Colab notebook. So let's start. So the first library is matplotlib.pyplot as PLT. That matplotlib.pyplot is the library, and PLT is the name by which we'll refer to the library instead of like typing out the entire library name. And import numpy as np. So this is like importing the library basically. Now we'll first start with creating a signal. Well, just as we talked about it, a signal is just information. But before creating a signal, let's create few other parameters. Like for example, to have a signal, we need few samples, right? Like you need to find out the velocity at few time intervals. Like how often will you find the velocity? So I'm like, let's create something called a sampling frequency and make it make it 1,000. Like over here, it's basically like I'll take 1,000 samples per second. So I'm measuring 1,000 samples and I'm measuring velocity 1,000 times a second. So this is our sampling frequency. And now we'll measure something, we'll define something called the time step. So basically, like time, since we are measuring 1,000 times in a second, time has to move 1 millisecond each time. So basically, like we'll make one measurement and then there'll be 1 millisecond gap and then the second measurement. So this will be 1 by fs. And there's nothing but time between two successive samples. Now we'll define the frequency of our signal. We can keep it anything that you want. For this set, for simplicity, maybe let's keep it 2 or something. That's fine. This is frequency of velocity. Like since over here we aren't measuring an actual velocity, but we are defining the function on our own. The frequency and the value of it can be whatever we want. And let's define the actual function of velocity. This is our input signal, basically x of t in the equation. Let's make it sine 2 pi into 2t. So first we have to put sine over here, and we can't use sine directly. Sine is a function in the library of NumPy. So we'll put np dot sine. So basically we are accessing the sine function in the np library. NP is nothing but NumPy. It's just a name that we put. And now again, we'll just put 2 into the value pi is also inside the library of NumPy. So we have to access it like that. And then again, star multiplication, f naught. F naught is nothing but the frequency of our velocity. And then t. T. Okay, but one thing is that we didn't really define time. So for defining time, what will we do is t is equals to, we'll use a function in the NumPy library called arrange. So np dot arrange. So here what does it do is that, let me type it first. So here it's basically between 0 and 1, I'm asking to make, like, it's actually not fs, it's actually ts. Like between, I'm asking it to make values of t between 0 and 1. So basically we'll take 1,000 samples in 1 second. So in 1 second, I need 1,000 values, right? So what TS does is that it goes from 0 to the next step, which is 1 millisecond. So basically it's like it starts at 0. It makes an array or a list of numbers. It starts at 0 plus TS. So it's 1 millisecond plus TS, which is 2 milliseconds. And so on till 1 second, which is 1,000 milliseconds. So this creates a list of numbers for us. And now we have created our signal velocity, which is x of t in the flowchart that I have shown before. Now we'll create the functional, like a functional, rather than exactly a functional, we can't write it over here, like in, because this code will represent it in a different form. Equation representing the system. Now this is the equation of the system. So this is x of t. And now basically we are doing the system part. So y of t, which is basically we are finding out acceleration over here. The output is acceleration. Acceleration is equals to, so because to get acceleration from velocity, we need to differentiate. We'll use a function called gradient. This is basically the derivative inside numpy. So again, np dot gradient, and this will take the input to be velocity. And also t, which is the variable over here. So basically what I have done is, this is y of t. Y of t is equals to d by dt of x of t. This is what basically I have written. And if you observe closely, this is sort of a functional. You're just giving an input of x of t and finding y of t. So you can write it also as capital x of t is y of t. So here, sorry guys, this is the functional and this is the output function. So, and how about the technical part? Let's do the plotting our signals. So for plotting, we're going to use the matplotlib. Firstly, something called fig.ax. Fig is nothing but the figure that we'll get, like the picture having the plots, and ax is nothing but the axis, is equals to plt.subplots. There's a function inside PLT called subplots. It basically enables us to make subplots. Like we can represent both the velocity and acceleration graph in a single picture. So since we'll have two plots, we'll make it two. And now, since there are two plots, there will be two axes. So to access the first axis information, we'll use ax0 dot plot. And plot is again a function in ax, which has the inputs of velocity t, our x-axis, and velocity, our y-axis. And repeat the same for x of 1 dot plot t comma acceleration. So this is what we use for plotting. And let's once run the code to check if there are any errors. Okay, this is our graph. So if you're confused which graph is what, let's do something. Let's put labels for these. So for putting labels, what we'll do is you don't need to do this on your own. I'm just putting it over here so that you'll understand better. Set title. Again, set title is a function inside ax0. This is basically the first plot. I'm going to set the label as velocity slash x of t. I'm going to put it again, x1 dot plot. Sorry, I made a mistake. Set title. Acceleration or y of t. Basically, this is the part. And if you're using any other programming platforms like VS Code or anything else, you can use you have to use another function called show, which basically shows the plot that you have made. plt.show. It's not really necessary for us right now, but let's still do it. Uh, there's a little bit of overlap because the image size is restricted. So basically, there is velocity or x of t, and this is the sine wave. As you can see, it starts at 0, goes to 1, and it has two parts. Like it goes from 0 to 500. It goes from a complete wave is done. So it basically repeats twice. And let's figure all that information apart. Basically, this is sine and this is cos. We sent a sine wave, we got a cos wave. So this is velocity information, we're getting acceleration information out. This is a broad, this is like this is like the code for signals and systems. This is a very simple example, but hope that made you understand on what it actually is. Let me show the flowchart again. X of t, our velocity gives into we give into the system. We get y of t, the sine wave, we get the cos wave. And the system is called a differentiator over here because it differentiates. If anyone has doubts, you can post it in the discussion group or the Q&A panel. I'll wait for a while for you guys to complete the code. I'll show the code over here. So I'm going to resume my uh, I'm going to resume the next topic. Since the code is pretty simple, I guess you're all done it. And then if and even if you haven't done it, just It's just sine wave. We get the output as cos wave. Nothing much to it. But just get the flavor of signals and systems. That's it. Okay, now we're going to start Fourier series. Like I said, Fourier series is a type of expansion. You might have known the Taylor series if they have taught you that in JEE. It's basically expanding a periodic function. The necessity over here is that it's a periodic function. And did you know about the school fact that you can express any periodic function as a sum of sines and cosines? Sines and cosines are together called the harmonics. So whenever in the session, if I say harmonics, I mean sines and cosines. So Fourier series allows us to represent any periodic function as a sum of harmonics. So yeah, like, okay, I heard it, but like how? Like, let's let's get to know, let's see it actually how it happens. So basically, Fourier series separates a signal into its constituent frequency terms. Let's see the formula over here, right? Once. X of t here is a periodic signal, and this is the formula for it. Like, it might seem complex, all this j, k, omega naught. Let's leave all that. All you have to see it, there are infinite terms, and there's a coefficient, and there is this e of t term over here. Like, don't think of it as some complex term, but just think of it as k omega naught. Basically, k omega naught is a frequency. K omega naught is like a discrete frequency. So as k omega naught changes, like k varies from minus infinity to infinity, this value changes. So we basically are writing x of t as a sum of frequency terms. This term over here, e power j k omega naught t, is nothing but a frequency term. Don't view it as a complex exponential. It's called a complex exponential because it's complex because it has j. J is nothing but root of minus 1. It's just I. But for convenience, we write j to prevent confusion from other terms like current and all. So over here, there's a complex exponential. This is basically a frequency term. We call it a frequency term because it has k omega naught. K omega naught is a frequency. And k changes. So basically, we are including all frequencies from minus infinity to plus infinity over here. And omega naught is the frequency of this periodic signal x of t, which makes it like there's a connection over here between these LHS and RHS. So enough about the formula. Like this formula, you can get back to it. You can try a few problems, but our goal is not to learn how to apply these. You can learn that anytime. Our goal is to visualize what actually happens in the Fourier expansion. So visualizing the Fourier expansion. Again, like I said, our goal is to write a function in its frequency terms. For example, in the previous example, we made a signal using the sine term, which had a frequency of 10. So its constituent frequency term would include a frequency like e power j into 20t. That would be its frequency term. Over here, if I give any signal to you, we should be able to write it as its constituent frequency terms. So we'll try out two signals over here. One is a rectangular signal and one is a triangular wave, triangular signal or sawtooth signal. So we'll actually see how does this Fourier transform, like a bunch of sines. See, like it's weird, isn't it? Sine is all smooth and nice. Let us see. Sine is all smooth and nice. How does this allow us to get any signal? Like literally any means any. I can even give you like a triangular, like over here, a triangular signal, which has like sharp endpoints. How are you able to get that just by using these waves? It's not that easy to understand, right? But let's actually see it. How are we able to get it? So, well, we are using Desmos to plot. We can even use Matplotlib, but Desmos is a little bit convenient and it has less error, so its plot are really nice to see. So, to plot on Desmos, you will use this. You can search on Google Desmos graphical calculator, or I'll share this link with you in chat in the discussion forum. So hope you guys can open Desmos. Well, you can obviously see Desmos, like what I'm doing over here. This is just for visualization. If you're actually interested on how do we use Desmos for plotting and all, you can see how do I do it. There isn't much math into this. All this is just examples. If you want, you can have it, or it's fine, you can remove it. So firstly, what we are trying to replicate is a rectangular way, which is basically like 1, 0, 1, 0. Periodic, obviously, because Fourier transform cannot replicate anything that's not periodic. So over here, what I have given is this is the Fourier series expansion of this. Like we got it using this formula. This is called the analysis formula. It helps you analyze a function. Analysis just means that you'll find these AK values. This is a term, this is just an exponential lesser frequency term. What is exactly unknown over here is an AK. Think about it. Like over here, we're writing it as a sum of all frequencies. That's fine. But like, what actually has all the information is AK. AK basically says that it has this much of a frequency. For example, if we take the sine wave amplitude is 1. So if we actually write its Fourier series expansion, I mean, it's already a sine wave, so there isn't exactly a Fourier series expansion to it. It'll just become sine. Its AK value will be 1 because the weight of the frequency of this 10 is 1. So you can think of this AK as a weight of each frequency. Weight just means like how much of a frequency is there. In sine wave, 100% of the frequency is 10 only. So this k omega naught becomes 10, and this AK, like since omega naught is also 10, because x of t period is 10, x of t is nothing but sine t, k becomes 1, and all the remaining AKs which are not 1 become 0. Because see, this signal does not have any other frequency other than 10. It's a pure frequency. It just doesn't have any other frequency except this. So if you take this and apply its Fourier series expansion, all you'll get is AK into e power something. E power something by Euler's formula, you can write it as Euler's formula, you can write it as sine cos theta plus I sine theta. So that is doable. Like we don't need to get to that. Basically, all I want to try to make you understand is that AK is the weight of frequency. And this example, the weight of 10, the frequency 10 will be 1, and all the other frequency weights are 0. Now let's get back to the example, enough of theory. So over here, we see the Fourier series expansion. We see a pattern over here. 4a by pi. 4a by pi can be taken common. So what we have is sine omega naught t by 1, sine 3 omega naught t by 3, sine 5 omega naught t by 5. So it's basically a sum of odd harmonics divided by their frequency. And if you're wondering what this A signifies, it's nothing but the amplitude of this rectangle. Since we are fine with 1, we don't care, we can just use A is 1. So first, let's put 4 divided by pi. To get pi, you just need to type P and I. Sorry, P and I, you'll get pi. To get from the denominator to the like to the normal typing part, you just need to press the side arrow, you'll get over here. Or you can take a cursor and press over here. Anything is fine. So now we took it common. What we're trying to see is we're trying to visualize how do signs, the seemingly smooth signs, help us get something as discontinuous not discontinuous, uh, something weird and sharp as a rectangular wave. Like rectangular wave is sharp. It's pretty different from the sine wave. So it's not very intuitive thinking how do we get the rectangular waves from the sine wave. So we'll try to visualize how do we exactly get it from the sine wave. So here we type the first sine term, sine t divided by 1. I mean, it's not necessary. I just put it for understanding that there is a pattern over here. And then there is sine 3t divided by 3 plus. Okay, let me first. I've done a slight error. Instead of t, because this is Desmos and we see over here that its x-axis is x variable. So it doesn't take in t. So x. Fine, nice. It plotted sine x into 4 pi. It's not exactly 1, it's slightly above. So now we add the next part, which is sine 3x divided by 3. So, okay, it seems a little weird, but it doesn't exactly resemble a square wave, a rectangular wave, right? And then now we add sine phi x, and we slowly see some resemblance. Sine 7x. You guys can probably stop over here. I'll just continue till a point where you can physically feel that there's actually a rectangular wave over here. So as we keep on adding terms, it just keeps getting more accurate. So now see, all I have done is add the frequency terms. What do I mean by frequency terms? Sine x, which has the frequency of 1, sine 3x has a frequency of 3, sine phi x has a frequency of 5. So I'm basically adding all these frequency terms to get this. And what do these coefficients mean? It basically says that in this rectangular signal, we have sine x, and the weight of sine x is 1. The weight of 3x is just 1/3. The weight of 5x is 1/5. The weight of 7x is 1/7. So basically, as we tend to infinity, the weight of the last term becomes 0. So that is the what is the significance of A of k in Fourier series expansion. And the more important thing over here is we made a rectangular signal out of just sine terms. You see, the value of it is approximating 1 and it's periodic with pi comma 0. So it's basically 1 0 1 0 1 0. If you go back and back, you can basically see that this is actually a rectangular wave. And we have successfully managed to replicate a sine a rectangular wave just by using harmonics, nothing but sines and cos. So let that sink in. And if you want to try it out or try in adding any cos term, or let's it'll get weird. But if you want to experiment, you can add anything. The software is in your hands. You can experiment around. I'll give a little of time if you want to ask doubts. If you didn't understand any concept, I'll repeat it. Just ask it. Basically, till now, we try to understand how exactly Fourier series manages to represent any function just by using sines and cos. Yeah. Hari Krishna asked, differentiating this doesn't give an approximate function of the original function differentiation. Okay, that's a good doubt. Uh, Differentiation of Fourier series isn't as direct as it is. Like, there are actually rules for it. If you read Fourier series in maths, you'll get to know more about it. For example, whenever there's a discontinuity, you'll take the output of this Fourier series differentiation will be the average of f x plus and fx minus. Like what this means is that since it's discontinuous, it will like basically take the previous value and the next value and then take the average of it to find it. Like if you are interested, you can look up to the math behind Fourier series. Over here, since this is just signal processing, we won't delve too deep into the mathematics of it. But yeah, differentiating it isn't as straightforward as it is. That's a good doubt. But that comes more under the mathematics behind Fourier series. This is how it helps us the signal process. What we're trying to learn is that how does this Fourier series, how does writing a function in terms of its harmonics, like in terms of its frequency terms, actually help us in signal processing? That's what we're trying to learn. Differentiating it, yeah, it's a good point, and it comes under the maths behind Fourier series. You can definitely check it out. Just Google Fourier series in Wikipedia or something. Or you can check out the book called Thomas Calculus. That's what we use for learning in our math course. It has it has a lot of rules. Like if I want to differentiate something, and there are limiting conditions for it. There are a lot of rules for it. So yeah, if you are interested, you can check it out. So now, since we are done with the rectangular wave, let's try out the triangular wave. The Fourier series expansion of triangular wave is this. It again has this term of 2 by pi. We can take that as common and a as 1. And over here, and basically, we have sine t and then sine 2 omega naught by 2, but it's minus. So we recognize another pattern over here. Let's type it out. Like I assume there are no more doubts. If you have any more doubts, you can put it in the Q&A panel. You don't need to worry. Just put any silly doubt. I'll explain it again. If I'm going too fast or you aren't able to understand, you can ask. I'll continue typing the part for the triangular wave. I think you've gotten a gist of what we're actually trying to do. So I'll be quick on this one because I won't bore you with all the specifics. Sine 2x by 2 plus. Okay, let me remove this for a clearer understanding. Let's see where we have started. We basically started at sin x, a normal, peaceful sine wave. And now we are slowly going to add the second term, which is minus sine 2x by 2. It gets distorted a little. Like, observe how it changes as we add one term after another. It's actually really fascinating. Even as someone who has seen this for almost 3, 4 months by now, it's still fascinating to me. 3. Sorry for that. Shit. Sine 6x by 6. So, if you want, you can add other terms, but I guess this sort of gives you the understanding of what it is. If you want to clearly see it, you can decrease the size of the x-axis to get a more clearer understanding of it. This basically changes the length of x-axis that is showing to you. So I'm just making it short so that, and we can even lock it to prevent any zooming in or zooming out. So now you can see this is starting to resemble a triangular wave. To give an idea of what a triangular wave is, triangular, just Google it, triangular, sorry for that, or sawtooth. There are a lot of types of it. The one we are discussing right now is this one. There's a sawtooth wave, not exactly the triangular, but the sawtooth is more appropriate. But for us, we don't care about the specifics, so triangular also works. So basically, we see over here, it repeats of every pi. Our signal is like goes down and starts again. It's a shifted version of this. So basically, see how we can recreate a seemingly vastly different signal just by using these sine and cos terms. Like over here, we haven't used any cos terms, but you get the idea. For other signals, we might need to use cos terms. So yeah, and again, let it sink in that we can recreate these completely different straight signals. So to put it into perspective again, we basically replicated the square and sawtooth signals just by using the sine signal, multiple scaled versions of it. And another interesting thing to notice over here. Okay, that's fine. Now I understand how does Fourier series work. Okay, it works. So, but another interesting thing, if you notice, is that we can actually tell that sine omega naught t and sine omega naught t, sine omega naught 3 omega, sine 3 omega naught t by 3, these terms are common in these two. So we notice that by seeing what are the coefficients of the frequency terms, we can see what is the overlap between functions. Over here, basically, if I put the two curves, you can see this part. Let me unlock the graph to zoom in. This part, the later part of the graph, is actually common. So we can broadly understand that what this minus part is doing is removing this part, this whole peak at zero. It's removing that and making it more sawtooth-like. And if you're wondering where the name sawtooth came, it's basically this looks like the teeth of a saw. Like, you know, a saw, right? It looks like a tooth of a saw, so it's called a sawtooth. Just a fun fact. So you can see, actually, this triangular wave has a whole square wave in it with few additional negative terms, which make it the triangular wave. So an interesting result of this Fourier series is that you can see what are the common parts or what are the intersections between two functions. Keep this in mind. Since you have plotted, let's proceed. Yeah. As you're talking about it, what's the big deal of this? Like, why are you making this big deal of being able to represent some random functions using sines and cos? Why do we need it? What is perfect purpose? Like, it's cool and fine, but where am I going to use this as signal processing? Seems too far of a stretch. So, yeah, this whole Fourier series gives us a new perspective. Let's see what that perspective is. There's a lot of text. Let me break it down point by point. The first thing is time domain is really irritating to deal with. We have seen that basically what do I mean is that, for example, let's come to this later. Time domain means that if you want to compare two signals, if I said compare the sine and cos, or sorry, sine, rectangular and the sawtooth, or I say compare this random weird signal and this weird signal, it'll be like, how do I compare it? Like you can say both are periodic. We are dealing with periodic signals right now, so that's common. But it's weird. Like all you have to do is just take each and every value at each and every point of time and then compare it, which is really cumbersome. What do I mean to say is that this time domain, which basically means x of t, the domain over here is time. The variable over here is time. So time domain is annoying to deal with. Further, we see that to extract information from a signal, we do many operations. One, the convolution that I said in the start of the session, all of those involve a lot of calculus. And if we proceed to move on in the direction of Fourier series in time domain, we need to do a lot of calculations. And advanced calculus is really annoying. Like you need a lot of data sheets about integrals. It's really annoying. So, but we noticed something that having this Fourier expansion, we were immediately able to say that okay, this rectangular wave and sawtooth have something in common. Like basically half of the triangular wave is nothing but the square wave, the rectangular wave. We were able to see that. I mean, you can even see that before. But what I'm trying to prove is that you instead of having to find out the like value of the signal at every time interval and then comparing it, all we are doing now is just looking at the coefficients, AKs. These values of coefficients, these weights, make it simpler. Basically, instead of looking at the whole time domain, we're just looking at the coefficients. So in this example, instead of uh, dealing with the value of this signal at each and every time interval, all I'll do is I'll take the Fourier transform, a Fourier series expansion of this periodic signal, and then look at its coefficients, and then compare its coefficients. Then I'll be like, okay, A1 and A3 are same, maybe. I don't know the Fourier series expansion of these. It might be complicated, I'm scared. So basically, all I want to say is that this whole Fourier expansion and these coefficients make it easy for us to analyze signals. So hence, I'm going to drop a new term on you called the frequency domain. So again, sounds complicated, but all it is that time domain is nothing but dealing with time dependent signals. X of t is in the time domain. Domain, like for example, if you're in math, if you're in Cartesian coordinates, the domain is x, y, z. Here, it's time domain. T is the domain. Similarly, I'm creating a new domain or I'm working with a new domain called the frequency domain. Basically, instead of dealing with time dependent stuff, we're seeing how the signal depends on the frequencies. So, okay, just keep that in mind. This Fourier expansion gave the idea of frequency domain. Again, frequency domain is nothing but the coefficients of these terms. This is the frequency domain. Over here, we look at this periodic square wave. This is from a book called Oppenheim, which is the reference book that we use. So if you're interested, you can ask. I'll share the PDF of the book, or you can just look it up in Google and see it. This is a square wave, and we're taking the Fourier series expansion of it, and we're plotting AK values. These lines that you're seeing is just AKs. You're wondering why is it lines? Because AK is discrete. You find AK values at 1, 2, 3, so on. So basically, you'll get this values, this load of values, and this is generally easier to compare. So get a feel of it. Basically, instead of comparing the value at each and every time point in time, we're comparing the AK values, comparatively less, just integral values. And generally, all these AK values tend to fade out at infinity. So that's also a really nice thing. We don't have to worry about the many things. You just have to look at this center point. So just let it sink. We are representing this square wave as this. And this is the frequency domain. This depends on k, which is the frequency domain variable, blah, blah, blah. Just understand this. There's a new term called frequency domain. If you have any doubts regarding the frequency domain, just keep it in. Let me bear with me and let me explain two more points, and hopefully you'll get a better understanding of the frequency domain. Basically, you have to convert the information in a signal into a function that depends on frequency. Again, like we said, working with frequency domain is a lot more helpful and simpler than time domain. And think of it like signals, for example, take sound. If you have high pitch and low pitch sound, to differentiate it, it's much easier if you have frequency. So instead of saying I have at 2 seconds, the decibel value is 10 and 20, instead of that, if I say I have frequencies 1 and 2, you'll be like, 2, I don't want two frequency, just remove it. And I'm saying just remove it, but how to remove it and all, you'll learn it later in filters. Filter and all is basically filtering, which is removing frequencies. You learn it in the next session. But basically, I just want you to get that frequency domain is helpful. Like time domain has few shortcomings. It's good, it's nice. Time is everyone's friend. Everyone knows time. But frequency is a lot more useful to work with. To cement this usefulness of frequency domain, I'm going to give an example. In physics, you might have read rotational mechanics and kinematics and all. There are Cartesian coordinates and polar coordinates. And when you come to rotational mechanics, we generally prefer to use polar coordinates. And whenever we are in normal kinematics and Newtonian dynamics, we prefer to use Cartesian coordinates. I mean, like, why? You can use just Cartesian everywhere, right? But you'll say polar coordinates are more useful. I mean, rotation dynamics means rotation. So rotation is more useful in polar coordinates, which has theta, right? R and theta instead of x, y. So that's why you use polar coordinates. Similarly, it's the exact same thing. Over here in few domains, frequency domain is a lot more useful. Using frequency dependent terms is a lot more useful instead of using time dependent stuff. So that is this whole new perspective of frequency domain that Fourier series brings us. To summarize it, the Fourier series gives us the idea of frequency domain to work in frequencies instead of time. Any doubts or anything? I might have gotten too fast and thrown a lot of theory points at you, but this concept is fairly theoretical. So, yeah, it's a bit tricky to understand. If you have any doubts, I'll help you understand it. Just drop a question in the Q&A panel. Uh, Someone wants to see the code. You can access it using the link that I have sent. And if you actually want to see the code, here is the code. It's a fairly simple code. This part is a recurring theme, this whole creating signal. Whenever we want to create a signal, we use this part. Think of it as an algorithm. We basically create a sampling frequency, then a time step, then time, then frequency of our signal, and then our signal. This whole part is a common part. And even if it's boring, I hope you guys will try to understand this. Just look into it, just feel it. You don't need to get all of the things I'm saying. I say a lot of stuff, but I want you to get the basic meaning of it, of that Fourier series is actually something cool and useful. So if he or she has seen this code, I'll move on. If any more doubts, you can ask it. So frequency domain. And okay, cool. Again, to summarize it, yeah, I am summarizing it a lot and saying a lot of stuff, but it's confusing. I had a lot of trouble understanding this, and I want to make it a little easier, hopefully, for you to understand. Series expansion gave us something called AK values, coefficients, weights of frequencies. So Fourier expansion gave us weights of frequencies to deal with, and that we feel is helpful for us in practical situations. And we chose to call this dealing with all these AK values or the weights of frequencies as working in the frequency domain. Applications. So, like I said, what we did over here is provide a common ground. a new domain. Common ground is nothing but a domain to compare signals. That we can just compare the Fourier series coefficients, the weights of frequency terms, to compare few signals. And this along with something called the Fourier transform, which is just an extrapolation of this concept. Extrapolation means extension, but just a technical term. It means we're just extending this topic to a broad number of signals, and then we'll get the Fourier transform, which we'll learn soon. Basically, that and this Fourier series is used in applications such as image analysis and shape recognition. As I said in the very beginning, what we did in the previous session, drawing boxes around shapes, that can be done using Fourier transform. Although it's a little outdated, it's still usable. Like Fourier series isn't outdated. Using Fourier series for this is a little outdated. Fourier series is not only useful in this, but even in a lot of complex math and all that. It's a really cool concept. I'll provide few sources that you can explore if you are really interested in Fourier series and what are its applications. So basically, the purpose is to create a common ground or a domain for easier comparison between signals and for easier analysis. And another straightforward application is for sound editing. I'm recording sound, there is some high pitched noise, some key sound, which has like some 10,000 kilohertz frequency, some really high number. So it basically renders your audio recording useless. So what do you do is send it through, take its Fourier series expansion. We find that there'll be some AK, which some A 10,000, that is the coefficient of sine 10,000, which is causing this entire noise. And we just use something called a filter that you'll learn in the next class to filter this out. Basically, subtract this out. I'm saying subtract, but it isn't that easy. It involves a lot of calculus and all. But Fourier series makes it a lot simpler by decreasing it to multiplication. So it helps in drawing shapes around figures, like shape recognition and image analysis, and also in sound editing to filter out unnecessary sound frequencies. These are few applications that to make you feel like Fourier series is actually useful. So again, applications. The one that I was saying, we are finding out what are the edges of this car by using Fourier transform. There's a really cool blog explaining about Fourier transform and its applications. If you're interested, you can check out this source. I'll share the link. It tells you the code behind this. It's a little complicated to cover in this video, so I haven't covered it. So basically that. And then Fourier transform, the elephant in the room. What is a Fourier transform? This is the actual final addition, you can say, of addition of the Fourier series. It basically helps you convert any signal into its frequency counterpart. So you have like you generally convert some function that depends on x, y, z into a function that depends on r, theta, and phi, right? In physics and math. Simply over here, Fourier transform trans basically transforms a signal that depends on time to a function that depends on frequency. That is, we convert a function into its frequency domain counterpart. So if you want to know how did we get this whole Fourier transform idea, it's by extrapolating the idea of Fourier series to aperiodic signals. We didn't talk about it, but one major disadvantage you can say of Fourier series is that it only applies to periodic signals. So by thinking about that, Fourier made a big assumption, like which turned out the introduction of this tool called the Fourier transform. He assumed that every aperiodic signal is periodic at infinity. Let it sink. Imagine this. You have a function, and what Fourier is saying is that this function is periodic but at infinity. He's saying that like imagine at infinity this function repeats. You just can't see it, but this function actually repeats. Sounds like bullshit, but it's just an idea. It's just an assumption. And by assuming that, what Fourier did is that basically in his whole formulas, he put that t tends to infinity, this time period, because of which he got this entire concept of Fourier transform, and he found these formulas which are used to form Fourier transform. Uh, cool formulas, little complicated. I mean, not really complicated. It's just integral. You can probably do it, but we won't cover it in this session. If you're interested, you can definitely check it out. I would recommend it. But we'll focus more on the intuition on this session. So again, Fourier expansion carries the information of weight of each frequency term, which is nothing but how much a frequency is present. Hence, Fourier transform finds the weights of each frequency. Basically, for any signal, if you send it to the Fourier transform, it transforms it into a function which shows you the weight of each frequency. Just keep this in mind. I'll show you we'll write a bit of code to get to know, to feel like what is exactly behind this. So, visualizing the Fourier transform. So, again, like I said, we get the weights of frequencies and saying it again and again. It might sound confusing, but that's what the Fourier transform does. And to make you understand it, I'm going to make a code that says you what does actually the Fourier transform? Like what part of the signal does it transform? So we do this by taking two signals, sine t and sine 3t. And we can even add a high frequency noise to the signal, and you can observe what changes are made. Basically, we'll take Fourier transforms of few signals using PyPlot, MATLAB. Sorry, library, Mathlot library. So time to code, open Google Colab, the same as before. I guess you probably have the link, and if you don't, check out the chat box or the discussion forum. This code is going to be a little complicated. I mean, not that complicated. We're just going to add a little bit of calculation part to this. Like if you don't want to open a new what do you say part, you can just add a new code block and click over here and start coding over here first. Or to make it a little simpler, I'll just cut out all this part and just paste it over here. And let's code over here. Again, I'm going to import. So I'm just going to copy this since it's the same. Like we have all these, right? So we're going to take all of these and paste it. As I said, this is the basis of any signal that we're going to create in matplot library in Python. So for anything, we have to define the sampling frequency and then proceed. So what are we going to do over here is we're going to define two frequencies. One is F0 of, let's say, 10. Like you can put anything, you can put 50 if you want. It's completely your wish. And F1, which is going to be 30. And I'm going to create a signal. I'm going to call it X of t. And again, I'm going to include the NumPy function. Sorry, I'm going to include the sine function from the NumPy library. So sine 2pi. Again, same thing. Why 2pi? Because basically, you might have seen this a lot of times, but 2pi basically, this whole thing is just 2pi omega t. It just makes the plot a little simpler and more viewable, easy to see it. You have 2pi, sorry, you have to put np.pi. Again, pi is a constant from the NumPy library. And then we're going to put f naught, f0, and t. And we have created the first term. And let's first do this, and then we'll soon add more terms to this. So we created our signal. Cool. Now we're going to, okay, let's first plot it. Plotting. Again, I'm getting lazy over here. If you want, I'll type it, but it's just the same thing. You can just create fig comma ex. Basically, this whole function of subplots has two outputs. Plt dot subplots has two outputs, figure and axis. Figure is information related to the picture. Axis is ax is the function related to the axis. So fig comma x is equals to plt dot subplots. And again, for now, we just are fine with one, so we'll just leave it like that. Later, when we have the Fourier transform also, we'll put two. So ax dot plot t comma x of t. And then I'm gonna put ax set title original or time domain. Now we're gonna, if you're wondering how to compile, sorry, I haven't said it. If you want to compile, you can press this button or you can just press Shift Enter. Shift Enter basically runs the code. So basically what you have done is that you have created a sine wave with frequency 10 and plotted it. Now the let's compute the Fourier transform of it. So Fourier transform. In coding, in NumPy, there's a function like, let me write it out. The Fourier transform is represented by capital X of, I'm gonna put F over here. F is the frequency. Since it depends on frequency, I'm gonna put frequency. And yeah, this is equals to, now it might seem complex, but just follow me on this. NP, which means NumPy, we're going to access f of t, comma f of t, dot f of t. And now we're going to input x of t over here. So basically, this is the code for accessing the Fourier transform in Python. There is like, if you want to know the meaning of behind these, I recommend to search NumPy FFT FFT. So this is the NumPy's official website regarding everything related to NumPy. So if you're interested or have any errors or are curious on how it works, you can check this out. So this is, so basically what this does is that it stores, like it basically does the Fourier transform of x of t and stores it in x of f. And I'm going to say something that might confuse or unsettle a lot of you, that x of f is actually complex. It might not be real, even if x of t is real, it might be complex. So it's important to take the magnitude of it, which I'm going to call absolute value of it. So ABS in NumPy, there's a function called absolute. You use it using np.abs, and then its input is x underscore f. And okay, fine. So okay, let's plot this. Now we have found it. So now let's plot it. So I'm going to change the subplots to 2. And I'm going to change this to the first value in the list. 0 means the first, and the same over here. So I'm very sorry. This should be 0 and this should be 1. 0, 0 depends, is the first one, which is x underscore t. And over here, let's put capital X underscore f abs. And now you might be like, okay, it shouldn't be t over here, right? Okay, fine. For this time domain, I put, let's change it to frequency domain real quick. For time domain, I put t. But for frequency domain, I should put f, right? But I don't really have f. What is f over here? So to get f, basically sampling, the samples of, uh, not samples, but the values at which the Fourier transform is evaluated. Again, NumPy at the Fourier transform. So we have to ask NumPy only for the values of f. So again, we use f is equals to np dot fft dot fft frequency. So this basically gives us the frequency values or an array of frequency values where the Fourier transform is evaluated. And its input is t dot shape minus 1. Shape is a function in Python. Like over here, we're creating uh, an array or list of values of t by arranging all these 1,000 values. So in T, all these 1,000 values are stored. What does shape basically mean broadly, not exactly? Minus 1 represents the final value. So instead of saying that I have 1,000 values, like 1,000 means how many other values that T have, shape basically gives how many values does T have. Shape is basically, you can think of it as the length of the list of values that T has. It just makes sure that f has this input just makes sure that f has the same number of values as t. So after that is done, let's change this to f and let's run it. And ta-da, this is what it is. Over here, we see that this is the Fourier transform. And you're like, what are these two lines over here? Seems weird, right? Basically, what it is that the frequency over here, f goes from 0.2 and all, but it's actually multiplied by 1,000 because our sampling frequency is 1,000. So since there are two spikes over here, ignore this part since we're taking the absolute value that's coming on this side also. Frequency can be negative. That's intuitive. Basically, this sign being the frequency being 10 over here, it create sorry 2 over here, it basically creates a bump at minus 2 also. So not 2 over here, it's 0.002, basically 2 by 1,000. So it creates a bump at 2 and minus 2. So I would kindly ask you to ignore all of the left side part of it. It'll just come over there also because it's a real signal. Like I said, we're taking the absolute value because of which. But what I want to notice is that, okay, I can't see that the frequency. I mean, since it's a simple sine signal, you can say this frequency is 2. But in this, I can clearly see that it has to. And now I'm going to give an example that is going to solidify your reasoning that, okay, Fourier transform is actually very useful. And sorry, I said that the frequency is 2. It's the 2 is of the previous part. The frequency of this is 10. So over here, it's 0.01, 0.001, sorry, because 10 by 1,000. So now we're going to actually see what we're going to make you realize what actually is the greatness of Fourier transform. Like, what is its utility? So again, I'm going to copy this entire sine part and paste it over here. And instead of F0, I use F1. So let me temporarily, for the time being, let me remove this part. Let me comment out. Hashtag is for comments. So, okay, now. Now you see that this is the signal that we're dealing with. This is the signal that we're dealing with. Seems very complicated. Not very, very. There are much more complicated signals. Like imagine you're going to record sound and process it, or you're going to receive calls from your friends, which is basically signal processing. When you receive a call from a friend, signals are being transmitted from their phone to the cell tower near you, from the cell tower near him, and then back to your phone, not back, from the cell tower to your phone. Basically, this whole thing involves bunch of signal processing and signal transmission. Like Sarthak said in the previous session, we have encoders, decoders, and all that stuff. Basically, in that, there's a lot of signal processing involved. And imagine if you're going to talk, there is going to be a lot of complex signals. It's going to be very weird, like the ones I showed over here. Our signals are going to be like this. I mean, the signal I'm showing over here is also not that less complicated. So I'm like, what are the frequencies in this? What are the frequencies that comprise this? I want to know that. And again, why do I want to know that? Because we got to know in Fourier series expansion that frequency related information is actually quite useful. So now I can zoom it in if you want to see. Now we have the signal. Now let's see what actually does this do. Let's run this. And now we have four bumps. Like the previous one, kindly ignore the left hand side and just focus on what's on the after zero. So at over here, there's a bump. What is this? It's nothing but 10 frequency or 0.001. And that is 30. And why is there a difference between the heights? Why? Because over here we see that the weight of the frequency having 30 is thrice as much as the weight of the frequency having 10. So since this part comes later, the bigger line, this must be the 31 and this is the 10 one. And you can see this is roughly thrice as much as this. I can't show you what does this point and what does this length actually mean, but I hope you get the idea of it. Over here you can see this is 500 and this is 1500. This is triple. So I hope you understand. This is what I mean the weight of frequency. It basically takes in a signal like this and gives out a simple signal like this. And if I wish to remove this signal, remove this high frequency 30 frequency signal, all I have to do is use a filter that removes any frequency higher than 10. Then these two bumps are removed. Because see, removing 30 frequency sine wave from this is relatively hard, but removing this bump is easy. I mean, I'm just asking you to feel it. If you want the proof for it, you'll get to know in tomorrow's class what do filters do and how frequency domain actually simplifies the calculation behind filters. So let me be quick. I'm dragging this on for a while. So again, to summarize it up, basically you have two signals of frequency 10 and 30. The sum of two signals, the frequency 10 and 30. The weight of the signal having 30 frequency is 3. And that is reflected in the Fourier frequency domain Fourier transform. Like Fourier transform shows that the weight of this is thrice as much as the weight of 10 frequency one. And whenever there's a frequency, there's a bump. And at all values, there's no bump. I just want you to feel this. And if anyone has doubts related to the code, you can drop your doubt in the chat box. Like again, this what we are doing over here is just adding two frequency terms and then plotting it to make you understand what a Fourier transform actually does. This is nothing but a simple example to make you feel that Fourier transform actually does something that's useful for us. If anyone wants to see the code, you can see it over here, or you can see it using the link I have shared in the group. Anything is fine. Okay, fine. Since there are no doubts in the chat box, I assume that you have either not understood anything or hopefully you have understood what I'm trying to review over here and have noted down the code if you wanted or understood the code. So let me summarize it up for anyone having any confusion related to this. A Fourier transform does nothing but give you the information related to its frequencies. Point number one is that when it comes to signal processing, dealing with frequencies proves really helpful in situations like filtering out noise and many other applications that you'll get to know if you will further look into signal processing. Like, I can't give much examples which are directly intuitive. I can say where it's useful in image analysis because like near edges where it changes, when we take the Fourier transform, in Fourier transform, all the pixels, like all the qualities of pixels, are much more easier to notice. Like the like similarly how in the previous examples, the information regarding like the weights of frequencies, it's much easy. Like Fourier transform of any image helps us see its qualities much easily. That's its application. And again, final summary. I know it's theoretical and confusing, but let me summarize it again. Taking the Fourier transform gives us the information about the weights of frequencies. It gives us a plot having the weight of each frequency and telling us what all frequencies comprise the signal. Like if I wanted to recreate this signal, what frequencies would I need and what is the weight of the frequency that I would need? And since, as I said in the very start, a frequency term is e power something, e power j something something. And you might have learned in your complex numbers in GE that sine e power I theta is nothing but cos theta plus I sine theta. Since we're using just sine theta over here, we are neglecting the cos part. There'll be some reflection in that because, like I said, over here we use complex exponentials for frequency terms. That is the very reason our Fourier transform is complex. I have a slide dedicated to why the Fourier transform is actually complex because that might be not very intuitive to a lot of people. So we'll discuss that. So yeah, let's get back to this later again. So now you got an understanding of what actually Fourier transform does. It shows you the weights of frequencies and what are the constituent frequencies. That's it. Basically, those two, the frequencies available and the weights of frequencies. And then now I'm going to show a screenshot. Okay, this might seem like, what is this? This seems really complicated and all. This is from a video by 3 Blue 1 Brown. He's an amazing YouTuber who makes videos on visual math videos. I would definitely recommend to check out his video on Fourier transform if you have the interest and the time. So Ignore this part, this whole complicated part. It's actually the logic behind Fourier transform. If you're actually interested to learn what is the logic behind Fourier transform, the very basics, I would recommend to watch the video because we don't have the time to tell this, and that would be delving too much into the theory as if this wasn't theoretical enough. So all I want you to see over here is that we have a pure frequency signal, a sine or cos wave, cos in this matter, of 3 beats. And over here, we notice peak. Like over here in our code, the peak was pretty straight. Over here, it's curved because if we zoom in, the peak over there will also be like that. But because it's heavily zoomed out and we took 1,000 sample points, the bump is like that. So basically over here, 3 beats is the frequency, and three is we see a bump at 3. That is basically it. And I want you to remember that. Like if you send a signal, the Fourier transform gives you what all frequencies does it have, and what is the weight of the frequency term. And now the final part. If you have any doubts, you can ask before resuming this final part. After this, we'll talk about convolution, and maybe if you didn't get the feel of what the Fourier transform actually does, I'll try to make it a little more simple without telling a bunch of technical terms. I'll try to make you understand it visually. Before going to this, please drop any doubts in the chat box. Why is the value 500 and how to find the Fourier series for different shapes? Hmm, interesting. Okay. And wait, before that, there is some error. IPython input in cell line. Like whoever has put this code error, you have forgot to put 2 in subplots. Let me show you. Over here, I put a 2 over here, signifying that I have 2 subplots in this image. Similarly, you have to put a 2 for, if you don't put a 2, AX will be just a simple array. That means you just have AX. If you put 2 over here, you'll have AX0 and AX1. That is an understandable error. It happens, just rectify it. You'll get the code. And if you have any doubts, you can ask me or refer to the code that I'm showing over here. The link is sent in the group. And why is the value 500 and how to find the Fourier series for different shapes? Uh, I'm assuming that attendance form will be shared soon. Let me answer this doubt now. Uh, I'm assuming that it's the Fourier series and not the Fourier transform for different shapes. And the value is 500 because it's like to get, I mean, it's just how the calculation is. You can change the value. This value doesn't signify anything mainly. Like you can, if you want it to be 1, if you want it to be the coefficient of this, you have to scale it down. Basically that. This is a rough plot and it doesn't ignore the specific values on the y-axis. I wanted to focus on the values on the x-axis. X-axis shows you where the bumps are there, where the frequencies are available. So that is important. That information is definite. Like over here, the if you are able to zoom in Google Colab, you can't. The bump will be at 10 and 30, which 10 by 1000, 30 by 1000, since the sampling frequency is 1000. So over there, bumps will be there. So that is definite. So I can explain why it's exactly that. But if you ask me about 500, there isn't exactly a reason for it. It's just that way. There's no specific reason to it. The more important thing is that it's triple. If one is 500, the other is 1500. I can even truncate this to be 100. Uh, then this will be 300. But for now, just the important thing to notice over here is that this is 500 and this is 1500. That's the important thing. That this is triple of this, and this is 30 frequency and this is 10 frequency. Uh, Show the total code once. Definitely. This is the total code. Do we even, is this enough or do we even want the previous one? To show the previous one, I have to zoom out. Again, if you want the previous code, you can open the link that I shared in the group. Just press the link. I have given the access for everyone to use to open that code. You can see that if there is some error, try compiling my code and try compiling your code. You'll notice some differences and you can debug it. Debugging is something that you have to learn in coding. Errors always pop up. You just have to run the code, check out for errors, and then debug it. It's fine. Yeah, cool. Uh, so then let's proceed. Why is our Fourier transform complex? That is the question. So yeah, it might be a little bit unsettling to know that Fourier transform can be complex, but I have given a little bit of reasoning in the code, so it might not be that much unsettling now. Like if the input is real, why the Fourier transform needs to be complex? A lot of people might have that doubt. I mean, why is this complex thing? It has haunted me enough during JEE. Has it come back? I mean, not really. If you actually learn about it, complex numbers is actually really fun and it simplifies a lot of things. It makes it very visual because of like the beautiful relation between complex like e power I theta and cos and sine. Whenever in many aspects, complex numbers offer a very beautiful solution to many mathematical problems. Over here, it is one such solution, and the problem is that, not the problem, but the situation is that in Fourier domain, the thing I've been blabbering on for 1 hour or so is that there's an amplitude. The amplitude is the weight over here. The weight of each one, like one person pointed it out, 500. That is the amplitude, and there is phase. That is one thing that we haven't been talking about. Well, I'll tell you don't need to know about phase much. In this simple examples, phase doesn't come into account. Phase is you can ignore phase, but phase is important when you remember we took the magnitude of the Fourier transform. Yeah, if you take the phase of it, if you find the phase of it, you will get to know that in this situation, the phase won't matter because we just have sine waves. They won't have phase. But let's first see amplitude and phase are two parameters in frequency domain. Like in this domain of frequency, we have two things that we have to worry about. One is the amplitude, which tells you the weight of a frequency, how much of a frequency is present. Is it very important? Is it 100% available? Or is it just zero point 0.1? Like, you might need to divide it by 5, maybe. We can talk about in percentages now then, or maybe divide it by 1,000 to get about percentages. Not exactly matters, but basically amplitude is weight, how much of that frequency is present. In the previous example, sine normal 10 frequency one was present for one third, not one third, was present for some 500 value. That's the amplitude. And the 30 frequency one was third of it. That is, the weight was thrice as much as this. So it's comparative, not absolute. Don't use absolute scale, use a comparison that if this is there this much, that is there thrice as much as this. Because imagine if you have only one signal, you don't need the weight of it. Because obviously, if only one frequency is there, the weight of it is 100%. But if you have two or more frequencies, then you need to know how much weight of it is there. Like if I have two frequencies over here, I got to know that the weight of 30 is twice as much as 10. So it's comparative, not absolute. So that is amplitude. And phase over here is basically offset. Imagine I'm speaking over here. I'm speaking calmly. And suddenly I begin to speak very fast in a very high pitch. So now a new frequency has been added to the signal of my voice. So basically, what that means is that till now, the signal is like periodic. It's everywhere the same. That at minus infinity is sine, at zero it's sine, at plus infinity it's sine. There's no phase for it. There's no initial phase. You might have no in SHM and all in physics. There was initial phase, right? Does the particle start oscillating at zero, or does it oscillate in somewhere between? So that is phase. Similarly, this frequency term, what is the offset or what is the initial phase of it? That's what this phase tells us. Over here, since we are dealing with simple things, phase is not an important concept, but it to make you get it, it's complex because there's amplitude and phase. And do you know what else has amplitude and phase? Complex numbers. A e power I theta. A is the amplitude, theta is the phase. So because of this resemblance between frequency domains parameters and complex numbers, we use complex numbers to deal with Fourier transforms. Complex numbers over here is nothing but a mathematical tool, and that's it. Do not be like, why is it complex? Did I make an error? Nothing like that. It's just a tool that we're using to make things more intuitive and more useful. That's it. So there's a reason why there's a complex number as a Fourier transform. If you have any doubts regarding this, you can drop it in the Q&A panel. We basically approach the end of the session. If you want, I can go over any of the graphs or codes to explain it again. Or if you want to know again what is weight and amplitude, or you might have missed any section of it, I'll repeat it. The session is close to its end. We'll soon share the attendance link. And there's a small concept called convolution, which I'll be talking at the end after this, after your doubts and all. So please drop your doubts. Uh, Someone is raising their hand. Maybe there's an error in the Q&A panel. Oh, it's working. So if you have any doubt, okay, cool. So I'll wait for a while. You can drop any doubts anywhere. I'm gonna wait. Someone is typing in the some discussion forum. I believe the Q&A panel is working, and if someone has any issues with the Q&A panel, then definitely drop your doubt in the discussion forum. I'm viewing doubts in that also. So take your time, think about. You can check out the codes. You can check out the graph in Desmos and how Fourier series basically helps us get seemingly very different functions just by using sines and cos. What is a fast Fourier transform? Okay, good question. I haven't explained about it. The FFT in the code is the fast Fourier transform. It's a function in NumPy. So basically, just a minute. Yeah. Uh, so basically, it's an efficient way to calculate the Fourier transform. Like it's just a way to compute the Fourier transform. It's nothing different. It's just a way that we choose to compute the Fourier transform. There are many ways to find it out. Fourier transform is just one. fast Fourier transform, I mean. It seems there's some issue with the Q&A panel. You can post your doubts in the discussion forum. And again, fast Fourier transform is nothing but a way to compute the Fourier transform. Over here, you can Google what is the fast Fourier transform. Again, it's not that necessary. It's not related to the concept of Fourier transform. It's more related to the math and the code behind it. So over here, fast Fourier transform is an efficient way to compute the Fourier transform of a function in NumPy in Python. It's just a library in Python. It's just a method of calculation. I hope you understand. Don't worry about the attendance link. We'll definitely send it. Again, if you're interested in FFT, I would definitely urge you to. There's actually quite few good videos on YouTube regarding what is the beauty of fast Fourier transform, regarding its efficiency and how does it help programmers to utilize the power of a Fourier transform. So again, it's just a tool. It's Fourier transform, but something that's used in programming. Yeah, there are a few. What does np.abs xf mean? Absolute means the modulus. Basically, as I told you, x of f, capital X of f means the Fourier transform. The Fourier transform is complex. So we can plot the phase as well as the magnitude of the Fourier transform. So over here, ABS is taking the absolute value, and absolute value for complex numbers is nothing but its magnitude. If it's raising doubts, I'll change this from ABS to MAG. MAG signifying magnitude. Again, you can plot the phase of it. There seems to be an issue in the NumPy library. If someone is interested in plotting the phase, I'll let you know how to plot the phase soon. Like right now, there's some issue in plotting the phase. There's a lot of error and the graph comes out to be complicated. But for now, for these signals, there is no information in phase plot. All the information is residing on the magnitude plot. And again, magnitude has the weights and the frequencies that are present. By the time the session ends, we'll be sure to send the attendance link by 1 o'clock or so. Don't worry about attendance. We'll definitely share it. Okay. Let me complete the convolution part, which will further cement the uses or the benefits of Fourier transform as a whole. And also, if you guys want uh, a bigger picture of the graph, I can share it at the end of the session. Like over here in Collab, you can't view the picture. You have to zoom it in. But if you want a bigger picture, you can use uh, editing platforms such as code writing platforms such as VS Code. VS Code is really popular. You can check it out for coding. It's a bit complicated to install and get started, but once you get started, it's really useful. You can code in any language. VS Code, if you plan to program in the future, VS Code is a really nice platform. If you want to learn how to use it, you can watch the lecture by a Harvard professor. He made a lecture on how to use VS Code. as a part of CS50 course. It's available on YouTube. I can share the link if anyone is interested. So let's go to the final part, convolution. So convolution is a concept that is in signal processing. So over here is the Wikipedia, an image from Wikipedia saying how, visualizing how what convolution does. This is basically what convolution is. You don't need the theory, you don't need this formula and all. Even if you plan to do this course, rather than this formula, you're going to use this graphical method a lot. This formula is only useful for theoretical questions or for any questions that require any conclusions from integration. So basically, what we're doing is we are taking one signal and flipping it and sliding it over the other signal. Basically, see, there is this F. Let's put F. Let's flip the signal G about the Y axis. And after flipping, we're going to slide it from minus infinity to plus infinity in this manner. Over here, I guess you can see what they are doing. Basically, it goes from minus infinity to infinity and nothing happens. And when it reaches this square pulse, you can see there's some overlap. And this overlap is nothing but the area of this overlap is nothing but the output of the convolution, which is plotted over here. So convolution just takes in one signal and takes in other signal and pops out a third signal. And this concept of convolution is used in something called convolutional neural networks, which is a subset of deep learning of in neural networks there is some in deep learning there's something called neural networks, which is similar to how our neurons work in our brain. It tries to replicate that. It's called neural networks. In neural networks, there's something called convolutional neural networks. And in convolutional neural networks, this is used. If you want to know one application of it, that is an application. What it does is basically it sort of tells you an overlap where multiple usages of this. There isn't any intuitive or some simple understanding that I can give that is in my reach. Basically, you can think of it as some fancy multiplication. It's basically multiplication. You are multiplying two. See, if you want to multiply 3 and 5, you just multiply it. 3 into 5, 15. If you want to multiply a function with a number, so 3 into some f of t, you multiply each and every output by 3. But say you want to multiply two functions. There are multiple ways to do it. If you directly multiply it, like, see, by a function, I mean a list of all the values it contains. So, for example, I have a function called 1 to 100, say. It stores a value of 1 to 100. It's basically f of x is equals to x. So it has 1, 2, 3, 4, so 100. And has something, say, step of x by 2. Basically, it means that at x is 1, it is 1 by 2, which is 0. The step of it is 0, right? So I have these two signals and I want to multiply these two functions. Signal function, same thing, interchangeable. So if you multiply it, what do we do is the first element of the first function is multiplied by all the values in the second function. The second function, like, right? If you multiply a plus b plus c into d plus e plus f, you get ad, ae, af. The first term multiplies with all three terms, second term multiplies with all three terms. So that is one way of multiplication. So when you have a set of values like these and when you're multiplying it, so instead of multiplication, there is one more useful way of multiplying. Overall, what you're doing is just multiplication. As you see, you're multiplying f of tau. Over here, this weird symbol is called tau. F of tau into g of tau, g of t minus tau. You're just multiplying, but in a different manner, in a manner that's more useful to us. Normal multiplication is not that useful to us. It can be useful in many situations, but in signal processing, mathematicians found that this way of multiplication is really useful. So hence came the convolution operator represented by an asterisk. The symbol is an asterisk. There are also similar fancy multiplications, you can say, called cross correlation and autocorrelation. This is basically when you convolute a function by itself. It's called autocorrelation. And cross correlation is the same thing, but you won't flip the function. Over here, you flip the function, because of which we gain the property of commutativeness. Basically, if you switch f and g, nothing changes. You can see over here, f convolution g and g convolution f is the same. But in cross correlation, g convolution f and f g, in this cross correlation, you don't flip the signal and just multiply it. In autocorrelation, you multiply the signal or convolve the signal by itself. Multiplication of the right is not the right term. Sorry. You convolve the signal by yourself. Here it's a different convolution. You don't flip it. And yeah, these are some three, you can say fancy multiplication, which are exclusive to signals and functions, which is just brought by mathematicians who thought that simple multiplication isn't useful enough. We want more tools. So yeah, these three are few useful mathematical tools. And if you want to know much about it, you can Google convolution. There is actually a really nice visual explanation on Wikipedia. Let me show you convolution. Over here, you see this is the square is coming, and this yellow part is the intersection, the area between these two. So basically, we are convolving a square pulse and this weird triangle thing. So when we convolve this, we flip it and we slide it. And as we slide, we plot the intersection area, which gives us this whole nice graph. This was the visualization of convolution. And so I'm like, why did you teach convolution in a lecture of Fourier series, you might ask? It's because you see this integral. It seems complicated, right? Well, it is. If you, as f and g get more complicated, this convolution gets understandably more complicated. An interesting thing that Fourier transform does is that when you take the Fourier transforms of f and g, you do not need to convolve. You just need to multiply. That's a really nice see. Imagine you don't need to convolute anymore to get the convoluted signal. You just need to use the Fourier transform and just multiply. It just cuts the entire process of computing this entire complicated signal integral. Well, okay, yeah. You also need to compute the Fourier transform, but it comes like it gives you another way. The Fourier transform is really simple. Then you do not need to go for this time-consuming process of convolution. Generally, generally Fourier transform is simpler. Sometimes convolution is simpler. Then you shouldn't go by that route, and you should convolve instead of doing that. So it's completely alternative ways. It's just making your life easier by giving you more tools to work with. So that was another benefits of using Fourier transform. It makes things like convolution, which are very essential to Fourier transform and many other fields such as deep learning, it makes it much more easier. It makes computing convolution much more easier. So that is one of the applications of Fourier transform. And overall, I'll say this one last time. Fourier transform is nothing but it tells you what frequencies are available in a signal and what weight is the frequency. Like how much of frequency is available and what frequencies are available. That's all it tells. And if you want to get more advanced, when phase is there, it even tells you when the frequency was added to the signal and when is it removed. Something like that. Not exactly that. That's just an intuitive explanation to what it is. So that's Fourier transform and Fourier series and convolution for you guys. So if you have any doubts, last few minutes are left of this session. You can drop them in the Q&A panel, or if that's not working, or if that's not responsive, you can drop them in the WhatsApp group. I will react it over there. Or what is the difference between Laplace transform and Fourier transform? Good question. Not good. See, Laplace transform is something that comes later. So it seems like if you look at equations online, it seems very, very different. But Laplace transform is nothing but you see the frequency over there that is there in the. Let me show you. Wait. In this Fourier transform formula, you see this omega over there. This omega. This is real. Basically, what do we tell in Laplace transform is that, okay, we just don't want real frequencies. We even will give inputs as imaginary frequencies. Again, why imaginary means imaginary numbers just have good chemistry with Fourier transforms and signal processing. So just we use that to get more information out of it. All we are doing is to make it simpler for us to squeeze information out of signals, because all signals are information. So Laplace transform takes this idea of Fourier transform and replaces this omega with s. S is omega plus j sigma, sorry, sigma plus j omega, where j omega is this thing, and we add a real part to it. Basically, Laplace says that we consider this as imaginary frequency, and we take this j omega and add some sigma t to it, making s, which is, let me show you the formula for Laplace transform. Sorry, Laplace transform. So yeah, this is the formula. Like I said, instead of j omega, we'll put s, where s is sigma plus j omega. J and I are the same. So again, we're just making the frequency complex to squeeze more information out of the signal. That is what Laplace transform is. It's fun. It's almost similar to Fourier transform, intuitively at least, but it has much more information that you can get out. There's something called poles and zeros, which is sort of out of scope of this session. If you're interested, you can look into it. Uh, there are amazing videos, visual videos on YouTube also. I can share the links to you personally if you want, or in the group. And the CUSG Advanced Higher Physics question based on convolution involving 2G functions. Nice, that's really nice. Well, convolution is a really beautiful concept. If you learn it graphically, it's really simple and really fun. So I guess they're just trying to introduce you to more practical concepts. Yes, attendance form, I think. Let me check if it's shared or not. Okay, yeah. We'll definitely upload it in a while. Just give us a little bit of time. We'll make sure that all of you guys get your attendance. Do not worry about it. So, meanwhile, as you work on attendance, you guys can drop the questions you have. I'll explain it if I can. Convolution is a simple concept. Like, I understand for if you get it in between of the exam, it's actually really hard to grasp. But if you're in a chill mind, if you look into it now, it's a really fun concept and easy to grasp. You don't need to worry about it. It's not that complex. And Laplace transform is just an extension of Fourier transform. It's it has more utility and reasonably it's more a little more complex. But once you get the feel of it, it's not much complex. It's a lot useful and it's a lot more beautiful because complex numbers is just visually, if you look at complex numbers, it is really nice. It has a lot of very useful and very intuitive solutions to a lot of complex issues. So yeah, we'll work on the attendance form. Just give it a little time. Meanwhile, drop your doubts either in the discussion forum or in the Q&A panel. Guys, we'll keep the attendance form open for an extended duration because it was sent late. Don't worry, all of you will get attendance. Just wait for a while. We'll send attendance in 2 to 3 minutes. The attendance form is shared. I have shared it on both the discussion forum and the chat, so check it out. Since if people have left the meeting as it was shared late, and I believe there are no more doubts, so I'll stop sharing my screen. And if you guys have any more doubts or are interested to know more about anything, you can definitely reach out to our team. We are open to doubts. We appreciate enthusiasm and like just reach out to us if you have any doubts. All right, so it seems it shows okay, I'll edit it. I think now you can fill the form. Just check it out once. So that's it, guys. If you guys want any link, I'll share it in the group so you can check it out from there. And we'll upload the slides in the meeting recording by evening. So, okay, that's it. The task will be sent by tonight, and you'll be given ample amount of time to complete it. And I'm going to end the session. Thanks for attending.